Hello everyone, I'm going to show you the results obtained from simulation and experimental validation of research dynamic matrix control for a single-phase inverter, carried out in association with Federal University of Rio de Janeiro and KU Leuven. First, start saying that this work is part of the project Mira Este Specific Innovative Microgrid Solutions, accounting for environmental, social, technological, and economic aspects for isolated rural areas of Ecuador, from the Research Group of Propagation, Electronic Control and Networking, PROCONET, of Universidad de las Fuerzas Armadas ESPE and KU Leuven with the support of Blur OS and the Belgian Development Cooperation. The presentation is structured starting with a brief introduction of renewable energy systems and inverter control techniques. Then, models and techniques considered to design the photovoltaic generation system are described. After that, the dynamic matrix control theory that was adapted to be used in a single-phase full-bridge inverter is developed. The results of the simulation carried out in MATLAB and Simulink are then presented. Following this, the setup and components of the system used for the experimental validation and its results are described. Finally, the most important conclusions of the work are summarized. As new economies emerge, the demand for electricity is increasing worldwide. This increase has shifted the attention of power producers to renewable energy sources such as wind, geothermal, hydro, solar, tidal, and biomass. However, in recent years, photovoltaic generators have stood out because of reduced manufacturing costs and their versatility to be mounted anywhere, an advantage that can be leveraged to reduce the use of fossil fuels in generation for remote areas and promote isolated microgrids. Inverters are one of the main components that compose the photovoltaic generation system. Several control methods have been used in inverters, including linear control techniques such as proportional integral based controllers, hysteresis control, artificial intelligence using fuzzy logic and neural networks, sliding mode control, etc. To guarantee system stability, the current research trend is focusing on the development of advanced control systems. One of them is Model Predictive Control (MPC), which consists of calculating a sequence of control actions that minimize a cost function or objective function. Dynamic Matrix Control (DMC) is an MPC technique that, according to the results obtained for control of other systems, offers a fast dynamic response, easy inclusion of nonlinearity system constraints, and the possibility to be incorporated a nested control in a single control loop. Moving on to PV generation system design, we start from solar cell, for which one diode model was used for its simplicity with acceptable accuracy, and its parameter can be obtained experimentally with simple and accurate techniques. On the other hand, the MPPT perturbance observer algorithm was considered, which consists of periodically varying the panel voltage in a certain direction with increments or decrements until it reached the point where it produced the maximum power transfer. It's one of the most used methods because of its simplicity and good performance. To complete PV generation system, a bus converter and a single-phase full-bridge inverter are used, starting from analysis in the state space model to dimension their components according to established generation capacity. Also, pulse width modulation is used to generate the activation signal for inverter transistors. Now, as previously mentioned, DMC technique is a type of predictive control which uses the open-loop step response of system model to predict the future behavior and minimize future error over an established prediction horizon. Following dynamical systems theory, the output can be expressed as the infinite sum of response coefficient time control variation. To make prediction of system behavior, we have to move k steps forward in the equation. Also, the estimated perturbances are added. If two expressions are extracted from this summation, one up to k steps and the other from k plus 1 to infinity, it can be noted that the first one estimates the future values and the second one calculates the past outputs. If future disturbances are assumed to be unchanged from present time disturbance, it can be replaced as measure system signal minus embedded model output. And if we know that this term is equal to the initial stated equation. Therefore, replacing the model output and grouping the sum of past values, we obtain the following equation. But if we look the prediction plot of system model, after n steps our system trends to a constant value, making this expression very close to zero, so the summation can be truncated up to n steps in the future. The sum of past values plus the measured inverted output is known as free response. Also, the resulting equation can be written in matrix form, composed of n number of rows equal to prediction horizon and n minus n plus 1 number of columns with m as the control horizon. This matrix is known as dynamic matrix. Now, a cost function is defined using a weighting factor to set the control effort and bring the embedded output signal as close as possible to the reference. Moving to its matrix form, it is then derived and equal to 0 to minimize the cost function. Finally, from taking control variation, DMC control law is obtained, which uses the vector of future reference, free response vector, and a K matrix obtained from dynamic matrix and weighting factor. Following with control law design is to form the dynamic matrix. With a sampling period of 1 millisecond and by applying a step-type input to the discrete time transfer function of the inverter model, it was found that from sample 20 onward, the model shows an stable response. Therefore, this value was set as the prediction horizon and 8 samples as the control horizon. First, controller performance was simulated in MATLAB using the discrete model of Inverter and a reference signal with amplitude 130 volts and frequency 60 Hz, obtaining the following results in reference tracking and disturbance rejection. The next step was to simulate the system using Simulink, programming the inverter with previously sized LC filter and the signal modulator. The MC control was integrated using a MATLAB function. The results obtained from both simulations shows that the inverter output is in phase with the reference used, produces a very low level of ripple, and has a very fast reaction to disturbance. To perform experimental validation, DSpace DS1103 controller was used to implement the proposed DMC controller and Typhoon Hill 402 hardware in the loop to implement single-phase full-bridge inverter and generate reference signal. Additionally, Typhoon Hill SCADA panel was used to create an interface with real-time model, with RMS voltage, RMS current, and total harmonic distortion was monitored. In a first test, DMC controller was tested by placing loads of 6, 12.1, 25, and 100 ohms. The voltage in all configurations is in range of 109.34 volts to 110.37 volts. In addition, the THD for voltage and current does not exceed 5% in any of the cases. In a second test, with a nominal reference voltage set to 110 voltage RMS, it's evaluated at transitions of 0.5, 0.25, and 0.1 per unit, showing a very fast reaction of controller, so that in case of abrupt changes, it can generate some overshoot, however the peak is not too pronounced. Finally, the feedback signal is suggested to 100 volts amplitude step type disturbance to demonstrate the controlled disturbance rejection performance. The system's dynamic shows an output voltage correction in a time close to zero point 0.1 seconds and a steady state response without offset error. So the results obtained in simulations and experimental validation demonstrates that DMC technique is suitable for control of single-phase full bridge inverters, standing out in fast reaction to variations in reference signal and presence of disturbance. In addition, total harmony distortion levels achieved with all loads have been kept below 2%, which improves the performance of many other control techniques. For more information or if you have any question, please contact me. Thank you.